In this set of videos, we're going to talk about a different model of trade. We've talked about the Ricardian model, and we've talked about the specific factors model. Now we're going to talk about a model called the Heckscher-Ohlin model, and this one is also known as the factor proportions model. If you think back to the Ricardian model, in that model we had one input, labor, and the gains from trade were driven by differences in labor productivity between the two people or the two countries. If you think back to the specific factors model, there we actually had three inputs, and there was a factor, an input that was specific to production of each of the goods. And so there, the only adjustable factor that we had, or input that we had, was labor. In the specific factors model, really what we were focusing on is how trade affected the distribution of wealth. So that model gave us the ability to understand why some people in an economy would support free trade and other people would not support free trade. This factor proportions model is in some ways going to be a little bit simpler. It'll be very similar to the specific factors model, but we're only going to have two inputs. The complication is we're going to allow infinite adjustment of those two inputs. So we haven't allowed anything quite like that in the first two models that we've looked at. What this model is going to allow us to do is to understand how the gains from trade can be driven by, or actually how trade can be driven by, the abundance of a factor that a country has. So if you look at a lot of countries, trade between those two countries is going to be driven by the fact that one of those countries is relatively abundant in some input. So for example, Canada exports a lot of lumber, and if you want to understand why, it's because they are relatively abundant in trees and lumber. So this model is going to give us a way of looking at how trade can be driven by the factors or the inputs that an economy is abundant in. So the Heckscher-Ohlin model is named after a couple of economists, like these things always are. We're going to have two countries. We'll have home and foreign. We'll have two goods, and we'll have two factors of production. Actually, sometimes you hear this model called the 2 by 2 by 2 model. So our two goods are going to be cloth and food, and then our two factors are going to be capital and labor. Okay, so let's go back to our Ricardian model. What we saw there when we had one input, when labor was the only input, our production possibilities frontier was linear. And then we talked about the specific factors model where we had two inputs. Actually, we had three, but in each sector there were only two inputs. And what we saw there is that allowed or created a situation where that production possibilities frontier was bowed out. Turns out with this model, as you would expect, the production possibilities frontier is bowed out. And since we've gone through understanding why that happens, we don't need to go through that again. What we do need to do is kind of identify some notation that we're going to use. In this model, we're going to use what we call unit input requirements. These are going to be like the unit labor requirements in a Ricardian model, but because we've got multiple factors, because we have multiple inputs, labor and capital, we're just going to call them unit input requirements. So these are what our unit input requirements are going to look like. We're going to designate the amount of capital that's used in cloth production as A with the subscript KC. Okay, that's the amount of capital used in cloth production. The amount of labor used in cloth production is going to be A with the L for labor, C for cloth. And then, as you can imagine, we'll have the amount of capital used in food production and the amount of labor used in food production. Now here's going to be the interesting thing. Let's identify a couple more things before we move on. So L we're obviously going to think of as designating the total amount of labor. And then we'll use capital K to designate the total amount of capital. that the economy has to work with. So now what we need to do is we need to think about the total amount of labor and how that amount of labor is used between cloth and food. Same thing with capital, the total amount of capital, and then how that capital is kind of distributed between cloth and food production. And the interesting thing here is that unlike the other two models that we've thought about, in those two models, the only thing that we had to think about in terms of production was labor. How much labor gets used in production of the two goods. Now we're going to have to think about the amount of labor and the amount of capital, and that's going to complicate things just a little bit, but it's not going to be too bad. So in terms of the basic model, it's going to work just like the stuff that we've already looked at. What we're going to end up having is we'll have a production possibilities frontier that is curved out. We can put the quantity of cloth produced, the quantity of food up here. Our economy is going to be able to produce any combination of cloth and food on or inside that production possibilities frontier, but clearly we're going to want to be on the production possibilities frontier. And the actual quantity, the actual combination of output goods that is going to be produced in the economy is going to depend upon the relative price of cloth to food, just like we've seen in our previous models. So what we've got is this ISO value line. Remember that ISO value line, we're going to end up at a point where the slope of this ISO value line is just tangent or equal to the slope of that production possibilities frontier. So in the economy, we want to maximize the value of production, which is illustrated by this ISO value line. So we want to move that thing to the northeast. And so we're going to end up at a place where those two things are just tangent. And if the relative price changed, remember the slope of this thing is the price of cloth divided by the price of food. I'm going to put a negative sign there because it's negative. If this changes, for example, if the relative price of cloth goes up, and that could happen because the price of cloth itself goes up or the price of food goes down or some combination of the two. If, let's suppose this ratio goes up, then this line will get steeper and we would move to a point somewhere over here where because the relative price of cloth went up in our economy, we now produce a higher quantity of cloth relative to food. So we've seen this before. That all is going to pertain to this model as well. What we need to do first is we need to think about how capital and labor are going to be chosen in production. And the way that we're going to do that is we're going to use what we refer to as an isoquant. So if you've had an intermediate microeconomics class or possibly an intermediate macro class, there's a chance they could have talked about it in there, then you may have heard of an isoquant before, but there's a chance you haven't heard of it. So what I'm going to do is clear this off and then we'll talk about what an isoquant is. All right, now let's think about production of our two goods. Let's focus on production of food first. So what I'm going to do is create a picture here that shows the input space. So this is going to be the amount of labor used in food production. Up here we're going to have the amount of capital used in food production. So points in this space are going to show combinations of the inputs. Sometimes you might have seen this just called labor produced and used to produce food and capital used to produce food. So you may have seen a picture similar to this where you've got labor and you've got capital up there, but we're going to use our A's here. So let's start with by thinking about a point on here. We'll call it point A. And this is going to be a combination. Point A is going to represent a combination of labor and capital that can be used to produce one unit of food. So if we look at the coordinates of point A, we're going to call this the amount of capital used in food production, we'll call it, let's give it a superscript A. And then this horizontal coordinate is going to be the amount of labor used in food production that corresponds to point A. So point A can be used to produce 1 unit of food. Now let's think about producing 1 unit of food with a little bit less capital. So what we've got now is a model where labor and capital can be substituted for each other. Now, the two inputs, labor and capital, are somewhat specialized, so they can't be substituted equally. So what we have to do is we have to think about using a little bit less capital. Let's move capital down in that direction, and then think about how much more labor we need to use to produce the same amount of food. So if you think about production of corn, production of corn is a good example where you're going to use some capital and you're going to use some labor. And the two inputs are substitutable. You can use more capital and less labor, or you can use more labor and less capital. You could plant the corn by hand and do a whole bunch of labor-intensive activities on it. But to some extent, those two inputs can substitute for each other. So let's think about reducing the amount of capital we use. Then clearly we're going to have to use more labor. Let's suppose that if we increase the amount of labor by that much, so that we get to a new point right out here that we'll call point B. Let's suppose point B is another way, another combination of capital and labor that can be used to produce 1 unit of food. So let's look at the coordinates of point B. So that's going to be the amount of capital over here used in food production that corresponds to point B, and then the amount of labor that is used in food production that corresponds to point B. So we've reduced the amount of capital and increased the amount of labor, and each of these 2 points can be used to produce 1 unit of food. Now let's do that again. Let's think about decreasing the amount of capital by the same amount. So I'm going to draw a little arrow down here that's the same distance as that one. And we'll be able to increase the amount of labor, but now let's think about how much labor we're going to have to increase by this time. You should be able to understand pretty easily that we're going to have to increase labor by more than we did when we moved from point A to point B. And the reason is that our inputs are specialized. They don't trade with each other or substitute with each other at an equal rate. So when we increase the amount of labor that we're going to use, because we're using less capital, we're going to have to increase by a bigger amount than we did here. And so we're going to move to point C. Okay? Point C is going to be another point where we are producing 1 unit of food. It's a different combination of labor and capital. Let's put the coordinates up here. So it would be A, the amount of capital produced in food production that corresponds to point C. And down here we've got the amount of labor used in food production that corresponds to point C. And what you can see here is that this thing starts to curve around like this. Actually, if we moved in the other direction, it would start to get steeper. If we connect these points, we get kind of a curve that looks something like this. And this is what we call an isoquant. Iso means same. Quantity stands for quantity. So these are all combinations of labor and capital that produce the same amount of input. So in our example here, I've been talking about this as if it's producing 1 unit of food. So if I wanted to label this isoquant, typically how we label it is we call it Q because it's producing some quantity of output. We put a bar over it to indicate that that quantity is the same. We're talking about food here, and this was the isoquant that corresponded to 1 unit of food. So we can produce 1 unit of food with a lot of labor and not very much capital, or we can produce 1 unit of food with a lot of capital and not very much labor. And there's an infinite combination of labor and capital that we can use to produce 1 unit of food. So now if we were to draw isoquants, we clearly aren't going to go through all of this process. Once you understand an isoquant, then we can just start to think about how different isoquants compare to each other. So if we had an isoquant, let's say this is Q bar equal to 1. Suppose this was the isoquant that corresponded to producing 1 unit of food. Here's the amount of capital used in food production. Then if we wanted to produce 2 units of food, let's say, clearly we're going to need more capital and more labor than to produce 1 unit of food. So the isoquant that corresponds to 2 units of food is going to be to the northeast of this isoquant that corresponds to 1 unit of food. Okay. So as we move in this direction, the amount of food that's being produced is going up. And as we move in this direction, the amount of food that is being produced is going down. And that should be easy to understand if you compare a couple of points on here. If you compare this point to, say, that point, then clearly this point has more of both capital and labor than this point does. So we're going to be able to produce a higher amount of output at that point than we would at this one. But keep in mind, that's going to be true for all of these points on this isoquant. This point, this combination of labor and capital, will allow us to produce a higher amount of output, 2 units of output, than any combination of labor and capital on this isoquant. Okay? So this allows us to think about how we're going to choose the combination of labor and capital that we use to produce a particular level of output. So now let's think about how we're going, if we were a firm, if we were thinking about how to produce 1 unit of output or how to produce 2 units of output, what's the optimal combination of capital and labor? Let's think about the objective now. Our objective is going to be to produce whatever level of output we want to produce at the least cost. So when we think about firms maximizing production, one of the things that typically in a principles class, if we were talking about principles of micro, we would talk about firms wanting to maximize profit. And that's fine. Firms do want to maximize profit. One of the necessary conditions for maximizing profit is that you're first minimizing the cost of production. You can't be maximizing profit if you're not first minimizing cost. So what we want to envision this problem as is a minimization. We want to figure out the least cost way to produce whatever level of output we want to produce. So what we need to do now is we need to think about what we're going to call an isocost line. And I realize we've got lots of iso value lines and isoquants and isocost lines. Just remember, anytime you hear anything like that, iso means same. So this is a curve that represents the same amount of output. An iso value line, I had one up here just a second ago, but that's combinations of output that have the same value. What we're going to do now is we're going to combine this picture with a line that shows combinations of labor and capital that have the exact same cost. It's going to be very similar, and it's going to look exactly the same as an iso value line. It would be equivalent to a budget constraint if we were thinking about the consumer's problem, if you've seen that before. But let's think about an isocost line. So isocost is going to be a line that represents combinations of labor and capital that cost the same. So let's talk about the cost of producing food. Let's just designate that with a C. The cost of producing food is going to be equal to the cost of the labor that we use plus the cost of the capital that we use. So let's start with labor. We're going to have the wage times the amount of labor used in food production. That's going to be the cost of our labor plus the rental rate times the amount of capital that we use in food production. So the total cost of producing whatever amount of food we want to produce is equal to the cost of the labor that we use plus the cost of the capital that we use. And again, W is the wage rate, R is the rental rate. This is the price of labor, that's the price of capital. What we want to do is graph this in this space. Okay, so what we've got up here is we've got the amount of capital solved for. It's on our vertical axis, so we need to solve for this term right there to put this into slope-intercept form, and then we can graph it in this space. So if we think about how we're going to do that, I'll do some quick algebra here. The cost of capital is equal to, I'm going to move this term over here, and then I'm switching everything around. This is equal to C minus W times the amount of labor used in food production. I'm going to divide through by R so that I can leave this by itself. So I get the amount of capital used in food production is equal to C divided by R minus W over R times the amount of labor used in food production. And now we can graph that. Let's just do it real quick. We've got the amount of labor, or quantity of labor over here. We've got the quantity of capital over here. If we graph this thing, it's going to have a vertical intercept. It's going to be downward sloping. It has a negative slope. It's going to have a vertical intercept of C over R. The slope of this thing, W over R, I'm going to put a negative sign out there because it's negative. You can't see it from the slope-intercept version of the line, but this intercept down here would be C over W. So if you think about what's actually going on in this picture, it should make sense. This number right up here is going to tell us the total amount of capital that we would be using if we were buying all capital. So if the cost was, let's say, $100 and capital cost, let's say, $2 each, then we would be using 50 units of capital. 100 divided by 2 would be 50. The slope of this thing, not surprisingly, is our relative wage. We've seen that before. And then down here, this number would be the total amount of labor that we're using if we were buying all labor. And any point on this isocost line would represent a combination of capital and labor that costs the exact same amount as every other point on this line. So this is a isocost line. It shows us all the combinations of labor and capital that have the exact same cost. It's the exact same idea as an iso value line that we've already seen. If we were thinking about isocost lines to the northeast of this, an isocost line up here would represent combinations of labor and capital that cost more than any bundle on this line. And of course, an isocost line that's closer to the origin would represent combinations of labor and capital that cost less than any bundle on this line. Okay? So our goal here is to produce a particular level of output in the least cost way. So what we want to do is reach the isocost line that's closest to the origin. So if we think about what this is going to look like, let's draw an isoquant. Let's just call it Q bar for now. Let's not worry about whatever level of output that stands for. Let's go ahead and label our axes. So we've got labor used in food production, we've got capital used in food production, and we want to produce this amount of food, whatever it is. Well, if we think about which of these infinite combinations of capital and labor we're going to choose, we want to choose the one that costs the least. So let's just pick a particular combination. Let's suppose we start with that combination. That is a combination of labor and capital that can be used to produce that amount of food. What we would then do is think about the isocost line through that point. Okay, so let's draw our isocost line, and let's suppose that that isocost line looked something like this. There's the isocost line. That tells us that the combination of all of the bundles of labor and capital that cost the same amount as that bundle. What we see is that there are some bundles of labor and capital over here to the southwest of this line that would actually cost less than this combination of labor and capital. Because we know that any isocost line down in here is going to correspond to a lower cost of production. So we could think, let's just move a little bit away from labor towards capital. So I just used a little bit less labor, a little bit more capital. Let's think about the isocost line through that point. It's going to be parallel to this one. So if we were to draw the isocost line through there, it would look something like that. And now we're producing the same amount of output at a cheaper cost than if we were right here, but we can do even better than that. And so what you see is that, of course, we're going to end up at a place where our isocost line and that isoquant are just tangent to each other. And this point right here, that point is going to represent the combination of labor and capital that cost the least amount that can be used to produce that particular amount of food. So if we look at the coordinates of that point, this would be the optimal amount of labor to use to produce that amount of food, and this would be the optimal amount of capital to use to produce that amount of food. We could give them a little star if we wanted. That combination represents, or that point represents the combination of labor and capital that is the best combination if we want to produce that amount of food. Now let's think for just a second about how that optimal combination would change if the relative price changed. Remember, the slope of this isocost line and the slope of that isocost line and the slope of this isocost line, all of those slopes are equal to W over R, the relative wage. Let's think about how the optimal combination would change if the relative wage changed. So let's again put labor used in food production down here. Let's put capital used in food production over here. Let's put an isoquant on here, Q bar. So we want to produce that particular level of isoquant, or that particular level of output. Let's suppose we start at an optimal combination given by this point. We'll call it point 1. We've got a relative wage right there. So we're going to start at point 1 with this relative wage, and let's identify the amount of labor and the amount of capital that we're using. I won't put the symbols down there, but these coordinates would tell us the amount of labor and the amount of capital. And now let's think about what would happen if the relative wage goes up. So let's suppose that we had an increase in the relative wage. Now that could happen for a couple of different reasons. We could have an increase in wage while the rental rate stays the same. We could have a decrease in the rental rate while the wage stays the same. Or we could have some combination of changes in these two things. But what we want to do is just think about what happens if that ratio goes up for whatever reason. The absolute wage and the absolute rental rate don't matter. All that matters is that ratio. So if the rental rate goes up, the relative wage goes up, then this isocost line is going to get steeper. And so let's suppose it does get steeper. We're still going to find our optimal point by looking where that isocost line is just tangent to that isoquant. And so if the isocost line gets steeper, our point of tangency is going to happen someplace over here, like point 2, where the slope of this thing, it's getting a little bit complicated here, the slope of this, let's call that the relative wage 1, and this will be relative wage 2. Don't look at that as squared. It's just a superscript that indicates it's the second relative wage. So if the relative wage goes up, what we see is that the optimal combination of labor and capital to use to produce that quantity of output now includes less labor and more capital. Not surprisingly, labor has become relatively expensive, so we would substitute away from labor towards the input that's becoming relatively cheaper, which in this example is capital. So now we understand how the optimal amount of labor and capital is influenced by the relative wage. Okay? If the relative wage were to go down, we would substitute towards labor and away from capital. So what we need to do now, I need to clear the board and then we'll kind of work with this and see what we've got. What we want to do now is we want to look at the relationship between the relative wage and the relative amount of labor and capital that's used in food production. So let's draw a new picture here that's going to summarize what we saw on the previous picture. On our vertical axis, we're going to have the relative wage, W over R. On our horizontal axis, we'll have the relative amounts of labor to capital that's used to produce food. What we saw there was that as the relative wage increased, we substituted away from labor towards capital. So if we were to draw the relationship between the relative wage and the relative amount of labor, we would see that it's downward sloping. Let's call that FF for food production. What we saw was that at a low relative wage, we used a relatively high amount of labor compared to capital. And as the relative wage increases, we substitute away from labor towards capital, so this ratio of labor to capital falls. And so this thing has a downward slope to it. We also need to think about the relationship between the relative wage and the relative amount of labor used in cloth production. And I'm going to draw a very similar curve to indicate cloth production. I'm going to put it to the right of food curve. What these two things are really relative factor demand curves. It shows us the relationship between the relative price of labor and the relative amount of labor used in food production, and this one shows it in cloth production. Now, by drawing that relative input demand curve for cloth to the right of the relative input demand for food, what we're saying is that at any particular relative wage, so if we pick a relative wage right there, we can look at the amount of labor to capital that's used in food production. It would be right here. And we could also look at the amount of labor to capital that's used in cloth production, and we would see that it's higher. Let's call this L, the relative amount of labor to capital used in food production. Let's just give it a superscript F there. And the relative amount of labor to capital used in cloth production, we'll give it a superscript C. And what we see here is that production of cloth is relatively labor intensive. It has a higher labor to capital ratio than production of food. So we would say that production of cloth is labor intensive, and we would say that production of food is capital intensive. Now keep in mind here that we're not thinking about, when we talk about production of cloth being labor intensive and production of food being capital intensive, we are not thinking about the absolute amounts of labor and capital used to produce cloth and food. We're thinking about the relative amounts of labor and capital. So capital intensity and labor intensity is defined in terms of the ratio, not the absolute amount. So what we need to do now is we're going to stop here. In the next video, we're going to kind of finish up how this economy works, and then we'll start to think about what happens when two similar economies start to trade with each other.